All righty. Sorry. Okay. So picking up from. Oh, hang on. Picking up from last class, we were talking about dynamically allocated memory. And so last class we looked at malloc and calloc, right? So the two memory allocation functions. There's a third one called realloc. So malloc gives you a block of memory that's uninitialized. Calloc gives you a block of memory that's initialized to all zeros. Realloc will try to reallocate a block of memory to make it larger or smaller. Right? Now, if you're trying to reallocate a block of memory, which is pointed to by a pointer, right, that means you can't have freed that block of memory yet, right? Because if you freed a block of memory, you can't do anything with that block again. Right? So in other words, if you have a pointer to that memory and you free the pointer, then you can't reuse the pointer. So you can't reallocate the memory that's pointed to by that pointer. The function looks like that. So it returns a void star pointer. Right? So the pointer is a pointer to the block of memory that's been allocated. It takes in a pointer. Right? So that's the pointer to memory that was previously allocated. So that's the block that you want to reallocate. New size, that's the new size in bytes of the block of memory. Right? It can be bigger or smaller than the original size. It can be the same size as well if you want, in which case nothing happens. New size is not allowed to be 0, though. So the standard says if you give a new size of 0, then the behavior is undefined. So it may or may not work. Okay, so on success, you get a pointer to the newly allocated block of memory. Right? So in other words, that original pointer that you gave it, the original pointer that you used, right? So that pointed to the memory that was allocated before. You can't reuse that anymore. Right? So you need to reassign that pointer back to the one that was returned by realloc. Okay? Now, if it fails, right? So if realloc fails to give you back a block of memory, it returns null. However, it does not deallocate the memory that was originally pointed to. So in other words, the pointer that you passed in is now still valid. Right? So you can still use it. It still points to valid memory. When you're done with it, you should free it. Right? So the only time realloc is going to fail is if there's not enough memory to satisfy the request. Right? Or if something strange happens. But if something strange happens, you really can't recover from it anyway. Okay, now if reallocation succeeds, right, then the original contents of the original array, they're copied into the newly allocated block. Right? So it really is reallocated memory. Right? Everything that was there is still there if the size is bigger. Right? If the size is smaller, then obviously you lose stuff at the end of the block. Right? If the block is bigger, if the block of memory of the newly allocated block is larger, right, anything that was newly allocated is not initialized. Right? So you can't guarantee on it having any sort of values. Right? But everything that was there is still there. So there's a little program that uses realloc. So instead of malloc and calloc, I'm going to make an array. So this is all the same as before. I'm going to make an array with malloc, right? And then I'm going to populate the contents of that array with the values 0, 1, 2, 3, 4, up to n minus 1. Okay? Now in the main function, it's the same. So I'm going to ask for an array whose size is less than 20. Right? I'm going to call makeArray to make the array and fill it up with values. And then I'm going to ask for an array again. So I'm going to ask for another array size. And now I'm going to reallocate that block of memory. Right? So if the result is between 1 and 20, I'm going to try to reallocate the memory that was pointed to by the original array. Right? So in other words, I'm going to make the array bigger or smaller. If I make it bigger, everything that was in the array should still be there. Right? And then all the excess memory will be uninitialized. If I make it smaller, I'm going to lose elements off the end of the array, but all of the other elements should still be there. Right? Okay, so here's my call to realloc. Right? So I store the result into a new pointer. Right? And then I check the result of the I check if the pointer is not null. right? So if our array means is that new pointer not null, right? If it's not null, I'm going to reassign my old array to point to the newly allocated block of memory. And then I'm going to print the array pointed to by ARR. Right? After that, I'm going to free the memory that was originally allocated to the array. Okay, so let's see what happens when we run this thing. This is array realloc. Okay, so we're going to make an array. Let's make an array of size 10. Right? Then we're going to print out the array. Right? So we have the values 0 through 9. And then I'm going to make a larger array. Right? So I'm going to reallocate the contents of this array into a bigger array. Right? So let's make an array of size 19. Okay, so there you see I have the first 10 elements. Right? Notice that I have a funny value here, right? Because this is the newly allocated memory, which is not guaranteed to have any particular value. So here it's got a funny value in it. I don't know where it came from or what it is. The rest of them are all zeros. Right? So any memory that's newly allocated, you can't count on it having any particular value. Now you can shrink the array as well. Right? So let's make an array of size 10. And there it is. And now I can reallocate that array to have size 5. Right? So in other words, I can keep the first 5 elements of the array and discard the last 5 elements of the array. And you get that. Right? So you can shrink or grow an existing array. Right? Sometimes when you grow the array stays in its same place in memory. Right? So if the memory allocator is able to find memory after your array, then it can give you back a pointer to the original array. Right? If it can't find memory after the original array, then it has to give you back a new block of memory that can hold all of the elements that you asked for. Okay, so those are the 3 dynamic memory allocation functions that we need to use. Right? Typedef is something that seems completely unrelated, but it's all going to come back in a minute. Okay? So Typedef. The Typedef declaration provides a way to declare an identifier as a type alias. Okay, so Typedef lets you make a new name. Right? That new name refers to some type. Right? So in other words, you can give a type a different name. Right? The reason you want to do this is because types in C often end up with really awkward names, really strange names, as you'll see shortly. Right? So you want to give it some simpler name that you can use to replace a possibly complex name. Now, it doesn't actually make a new type. Right? So it's not like making a class in Java where you create a new type. Right? All it does is make a new name. That name happens to be the same as another type. Right? So the syntax is typedef type, so that's whatever type you want to give a new name to, right? And then alias. And then there's a semicolon at the end, which is missing. So alias is going to be your hopefully shortened or easy to remember name. Right? So type is an existing type. Alias is the new alias for the existing type. Some of these types that we've been using, size type anyway. Size t, which you've seen a few times, right? So that's the size of any object in C. That's the type that's used to represent the size of any object in C. It's actually a typedef, right? It's not its own type, right? Size t is actually long unsigned int on my computer anyway, right? There's another type called pointer difference type, right? So that's what happens. That's the that's the type you get when you subtract 2 pointers, right? So it's the difference between 2 pointers. So that type is actually long int, right? It doesn't actually have its own type, right? It's just a name for some other type, right? The reason you do this is because you want to avoid writing complicated types, right? And it also lets you do something in C which you can't do in Java. So you can actually provide a name for an incomplete type. Right? So let's look at that. Okay. So the first example, typedef int star int pointer type, right? So pointer t, that's my alias, right? So anywhere I use the name int pointer t, I'm actually saying that's a pointer to int, right? So that's actually an int star. Right, so I'm going to show you an example of that in a second. Here's one that we're not going to use for a couple of weeks. This is a pointer to a function. Right? its syntax is really bizarre, so you have to get used to this. Sorry, I have a scratch here that I can't reach. An itch. Ugh. Sorry. Okay. All right. F pointer t. So that's the name of my alias. Okay. F pointer t is the name of the alias. So if I write F pointer t, what that means is it's a pointer. So that's what the star is there for. It's a pointer to a function. Right? That's why you have the other round brackets with these two types in it. Right? So F pointer t is a pointer to a function that returns an int and has two int parameters. Right? So in C, you can take pointers to functions. Right? And this turns out to be extremely useful, as you will see in a couple of weeks. Right? So for now, that's your first exposure to a pointer to a function. Right? Looks weird, you have to get used to it. Here's an example of an incomplete type. Right? So here I've got Typedef struct list. Okay, so that name list is the name of a type. Sorry, it's an alias for the type struct list. And I'm going to tell you what a struct is in a couple of minutes. Right? I haven't actually, there's no definition of what this struct list thing is. Right? I'm just saying that whenever I use the name list, I actually mean struct list. Right, so how about this int pointer type? Right? So remember int pointer type, whenever I use that name, that actually means int star. Right? So pointer to int. So I can go back to that malloc example. Right? Everywhere I wrote int star, I can now write int pointer type instead. Right? So int pointer type array, that's the pointer returned by malloc. Right? So it's just a pointer to int. When I make my array, right, by calling make array, I can just store the result in a pointer, in a variable of type int pointer type. Right? So I don't have to write int star here. Right? I can actually write out something like this. Right? This is not a particularly useful example, right? But it's just showing you how you could use a typedef. You'll see a much more useful example in a minute. Okay, so typedefs create new names, and the names just are aliases to existing types. Structures. Okay, so a structure or struct in C consists of one or more members, variables, whose storage is allocated in some ordered sequence. All that means is a structure is a block of memory. It's got a bunch of variables in that block of memory. Right? So a structure is just a group of variables in one block of memory having a single name. Right? And so if you think about this for a second, this sort of looks like a Java class that has no methods. Right? And so in other words, a structure is like declaring a bunch of fields for a class in Java. Right? It's just the fields. So your syntax is struct. Then there's something called a tag name, because structures are strange. And then inside the pair of braces is just a list of the variables that you want in this structure. Right? So it's a type followed by the name of the variable, semicolon, type followed by the name of the variable, semicolon, and so on, and so on, and so on. Right? So what is this tag name thing? So the tag name is not actually a type. That's the weird, oh wait, here, I'll give you an example first. So here's an example of a two-dimensional point implemented as a structure. Right? So a two-dimensional point just has an x and a y coordinate, right? So I can declare a structure called with the tag name point2. Right? Inside that structure, there's two variables x and y. Right? And they have type double. I can make a variable called p whose type is struct point2. Right? So point2 is not a type name, at least not yet. Right? Point2 is what's called a tag name. So it's a name that belongs to a structure. You can think of struct followed by a tag name as being the type. Right? So struct point2 in this case is the type. Right? So my variable p is a variable of type struct point2. Right? Notice that there's no initialization. Right? Just a semicolon. So for a structure, if you don't initialize the values of the variables inside the structure, they get their default initialization values. Right? So for numeric types, you get the value 0. I can get access to the variables in the structure using the dot notation. right? So if you're wondering where Java got its dot notation from, well, this is it, right? So p.x means the x variable belonging to the structure variable p, right? p.y means the y variable belonging to the structure variable p, right? And if I print these out, you get 0, 0. So this is struct point 2. Right? So you get the point 0, 0. Right? Anybody got any questions so far? So the easiest way to think about this is it's just fields belonging to a Java class. Right. All right. So the tag name of a structure is not a type, right? The tags exist in what's called a namespace. So it's actually a different namespace than identifiers such as variables, typedef names, and function names. Right, so all of your variables that are in a function, for example, right, when that function runs, there's a namespace for that function. Right? The namespace is just the space of names that are in the function. Right? All of your local variables go in that namespace. Any structure tags are not in that same namespace, so they exist in a different namespace. What that means is you can have a tag and a variable with the same name. Right? So I can have a variable called point2, or I can have a typedef called point2, and I can have a structure with a tag point2, all in the same program. Right? So when you're working with structures, the type of the structure is, this type of variable that you make is struct tag name, which gets really awkward to write, which is why you want to use a typedef. Right? So here, oh wait, why is this here? It's not right. Oh, there we go. Okay, so this is the previous example, right? Here's the same example written using a typedef. Right? So there's my structure, declaration, definition, I guess, because all the variables here. Then I can write type struct point2, point2. Right? So notice you have a tag name and a typedef name that are the same, which is fine. So in C, that's allowed, right? Because the tag names, they live in a different space than all of the other variable, typedef, and function names. Right? But now what that means is I can use the word point2 as a variable type. Right? So instead of writing struct point2 here, I can just write point2. Right? And now this runs exactly the same as the previous program. Right? So this is exactly the same as the previous program. It's just rewritten using a typedef. Okay. Now, can you initialize members to a structure? The answer is yes. Right? So C doesn't have constructors like Java has. Right? But what C does have is that it's got this array initialization block. Right? So you can initialize a structure using the same syntax that you would initialize an array. Right? So the values for all of the members of your structure, they can go inside of a pair of braces separated by commas. Right? C99 does not let that list of initializers be empty. Right? So you can't write point2p equals empty braces. Right? The compiler will complain. If you want to, you can actually say what the member variable names are when you do the initialization. Right? The syntax is a little funny. You have to put dot in front of the variable names. So I'll show you an example of that in a second. What's also funny is that the order that you initialize your member variables in doesn't have to match the order that they're declared in the structure. Right? If you don't explicitly initialize something, it gets 0 initialized. So that means all the numeric values get set to 0. If you have a Boolean value, it's also 0, right? Because Boolean's also an int. Pointers get initialized to null. Okay, so here's my structure up here. Right? Same structure as point2. There's my typedef. Right? The first point p is initialized to the point 3. Right? So px gets the value 2. Py gets the value 3. Right? Q is where I'm actually saying what the individual members, I'm actually assigning values to the individual members. Right? So inside the brackets, it's not x equals 1, it's dot x equals 1, right? And then it's dot y equals 1.5, right? If you want to, you can reverse the order of them, so the order doesn't have to be the same, right? And if you don't initialize one of the members, then the member gets initialized to 0. So R sets r dot y to minus 3.1, r.x is not explicitly initialized, so it gets the value of 0. Right, so if I run this, I should get 2, 3, 1, 1.5, and 0, minus 3.1. Right, and you do. Right, so p is 2, 3, q is 1, 1.5, and r is 0, minus 3.1. Right, so that's how you can initialize the members of a struct. Right, you don't have to do it this way, right? You can do it the way I did it before too. Right, so instead of doing initialization, whoops, where'd it go? Oh wait, I never did it. Okay, so never mind. I was going to say you can just say after you make your variable, you can write px equals 2 and then py equals 3. Right, so that's fine too. Accessing members. All right, so if you have a struct object, you can access the members using the dot operator. Right, so just as I've shown you so far. Now, a lot of the times when you're working with structures, you don't have the structure object directly. What you have is a pointer to the structure. Right? So if you have a pointer to a struct object, you can still get access to the members. You just use a different operator. So you use hyphen greater than to access the member value, the member variable. Right? So what that does, it automatically dereferences the pointer for you. Right? So you've got a pointer to a struct. Normally you'd have to dereference it. Right? If you use minus greater than, that dereferences it for you and then gives you access to the member. Right? You can, if you want to, manually dereference the pointer. And I'll show you an example of that also. Right. Okay, so again, there's our point2 struct. There's our typedef. Right? Here's my point23. I'm now going to take a pointer to my object p. Right? So pointer now points to the point object having the coordinates 2, 3. Right? And now I'm going to use the minus greater than operator to access the x variable belonging to the structure. Right? So pointer minus greater than x says set the x value of the object pointed to by this to 200. Right? And then set the y value to whatever this points to, which is up here, right, to 300. Right? Now if you print out p again, you'll get 200, 300. Right? So p was 2, 3. Then I take a pointer to it, change the value of its members using the pointer, right? And then you can see that if you use p again, well, the values of x and y have changed. Resume. Okay. Any questions so far? All right. Assignment. So can you assign two structures? The answer is yes. Right? So if you write q equals 0.2, q equals p, right, that actually works in C. What you end up with is a member-wise copy. So what ends up happening is all of the individual members get copied using assignment. Right? If the struct contains a pointer, right, then you have two structure objects with a pointer that points to the same object. Right? So it doesn't dereference the pointer and then copy the object for you. Right? If you want to do that, you have to do that yourself. So there's my point P. Right? Let's do 3. Here's my point Q. Right? It's not initialized. So if I print it out, it's going to be 0, 0. Right? Now I write Q equals P. Right? So what happens is Q dot x gets assigned the value P dot x, and then Q dot y gets assigned the value P dot y. Right? So member-wise copying. So if I print out Q, you're going to get 2, 3. Right? If I change Q, right, by changing its x and y members, right, then the value, then Qx and Qy change, but Px and Py do not change, right? Because you actually have two separate structures here, right? You actually have two objects here, right? So in this example here, P will still be 2, 3, but Q will now be 200, 300. Wait, that's not right. Okay, so let me go back to the slide. Okay, so we print out P, so it should be 2, 3. And it is, right? Then we print out Q. It should be 0, 0. And it is, right? Then we say Q equals P. So Q should now be 2, 3 as well. And it is, right? Third line. Then I change Q, right? So I change the coordinates of the point Q. And I print out P and Q, right? So P does not change. It's still 2, 3. Oops, sorry. P is still 2, 3. Q is now 200, 300. Right, so you actually have two separate point objects here. All right, can you dynamically allocate a struct? The answer is yes, right? So if I want to use malloc or realloc or calloc, right, I can allocate the space for a structure, right? You just use size of to get the size of the structure. Right? So for example, instead of writing point2p equals something, right, I now make a pointer, and then I use malloc to give me some memory to hold the pointer, to hold an object of size 0.2. Right? Then I use, now remember when you use malloc, the memory is uninitialized. So the coordinates of that point could be anything. Right? So if you tried to write p.x and p.y, p hyphen greater than x and p hyphen greater than y, you could get anything. Right? So instead, I assign values to them and then print them out. Right? Notice that when you use p, though, it's a pointer in this case. Right? So to get access to the members, you have to use the arrow instead of the dot. Right? So this is going to print out 100, 200. Right? Which isn't surprising. Okay, so you can use malloc to get space for a structure. Now, what you cannot do is you cannot check if two structure objects are equal. Right? So C has no built-in mechanism for comparing structs for equality. Right? So in other words, equals equals and not equals are not defined for structs. Right? So if you try to write that, the compiler will flag that as an error. Okay, so what happens if you need to do this? So for example, what if I want to check if 2 points are equal? Then you have to do it manually yourself. Right? So if I need to do this, then you have to decide what does it mean for two structure objects to be equal. Right? For points, it's easy, right? Their x and y coordinates have to be the same. Right? But you have to do this manually now. Right? So if you want to do this more than once, you're going to want to write a function, which is why the equals operator exists in Java. Right? So if I want to check, so here's P, right? I guess I allocated it with malloc here. So it's the point 100, 200. Q, I'm going to initialize to the same x and y coordinates, right? And now I want to check if P and Q have the same coordinates, right? So here, I'm manually dereferencing P, right? So instead of using the arrow operator, I'm manually dereferencing the pointer and then using the dot operator. Right? This is why no one manually dereferences a pointer to a structure. Right? You just use the arrow operator. But you can if you want to. Right? So I can dereference P, put it in round brackets, and then that gives me the object pointed to by P. Right? So I have to check, is Px equal to Qx and is Py equal to Qy? Right? And if they are, then I can say that they have the same coordinates. Right? So does this work? Well, the answer is yes. Right? So P and Q have the same coordinates, right? Which is not surprising, right? But again, if you're going to be comparing points for equality a lot, you should write a function, right, and call the function. Okay, now organization of a C program. So today I'm just going to use the point2 point2 struct. On Wednesday, I'm going to actually implement a full-blown list. Right? And that's actually fairly complicated. So that's probably going to take 2 days to do. So organization of a C program. All right, so what I've basically done here is I've basically created a new type. Right? That's more or less what I've done. So the type is 0.2 in this example. Right? Now I've created this type. Right? It's just an x and a y coordinate. right? But already we've come across the situation where you might want to make a function to check 2 points for equality, right? And you can imagine there's a whole bunch of other functions that you might want to write that operate on points, right? So in other words, I have this type, and I've got a bunch of functions associated with the type, right? Now, if this was Java, you would just write a class, right? The fields of the structure would go into the class, and then the methods, the functions that belong to those fields or that are associated with those fields, you would write as methods, right? So you'd bundle everything up into a class. C doesn't have any classes, right? So you have to do something else in C, right? So what you do in C is you take your type and you plunk it into a file called a header file, right? Then you take all the functions that you want to write that operate on that type, and you put their function declarations in the header file. You don't put their definitions in the header file. You just put their declarations, right? A header file normally has the extension .h in C. The compiler doesn't actually care what you call it, but every other C programmer will care, right? So when you make a header file, it's normally .h in C. Right? Now, any C source code file that uses your type, all they have to do is include the header, right? And now they get the type of your, I guess they get the typedef of your type, and they get the list of all the functions that they can call using your type, right? They don't get the definitions, they just get the function prototypes, right? But that's all the compiler needs to compile a program. The definitions for your functions you put somewhere else, right? So you put it in a separate C source code file, right? So I'm going to take this point2 struct, and I'm going to break it up into two things, right? So I'm going to make a header file, and then I'm going to make a called point2.h. I'm going to make a source code file called point2.c. Right? So what functions do I want to implement for my point my point struct? Right? So you could cook up literally hundreds of these functions, right? I'm just going to do 4, I guess, right? So I'm going to make a function that lets me move a point, right? So it's called move. It takes a pointer to a point, and it takes 2 double values, dx and dy. So it moves a point by the vector dx, dy. Right? In other words, it adds dx to the x coordinate, it adds dy to the y coordinate. Now, why does it need a pointer to a point 2? So why can't I pass in just a regular point 2 if I want to move the point p? Anybody? 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 Someone must know. So C uses pass by value, right? So when you pass in a structure by value, you get what? Right? All you get are you get the structure, so you get the members of the structure all passed by value, right? So when you pass if this was just P, right, you don't get the actual object that you want to move, right? You don't get the actual point object you want to move, right? You get a copy of the point object that you want to move. So you end up moving the copy, right? But that doesn't actually change the original point object, right? So if you want to change the original point object, you need to pass in a pointer to that point object, right? Okay, so multiplies that the coordinates of this point object by s, right? So that lets you scale a point or mirror it if the s is negative. Here's equals. So I want to test if 2 points are equal. So now I don't need pointers here, right? All I care about are the x and y coordinates of p and q, right? It doesn't matter if I get those via a pointer or via a copy, right? It's going to be the same thing either way, right? These are marked as const, even though they don't have to be, right? So remember what const means. Const means that I can't change the objects pointed to by p or q in this function, right? So in other words, I can't write p.x equals something or q.x equals something. Not that it would matter anyway in this case. Finally, I've got point to string. So this is going to give you back a string representation of the point, right? So this will be the analog of Java's toString method, right? You're going to see what happens when I write this method. You're going to see that it's really, really awkward to write, and you're going to wish this was Java again, right? Okay, here we go. So you're going to make a header file. That's the first thing we're going to do, right? I'm going to make a header file. I'm going to put my typedef in the header file. I'm going to put my function prototypes in the header file. Now, the way that C works, so when you include a header file, right, in your program, it literally takes the header file and copies it into your program, right? That's literally what it does. If you copy the header file into your program more than once, that's illegal, because you end up with, in this case, you're going to end up with the .2 typedef showing up twice, right? And you cannot make a typedef with the same name, right? So you have to prevent a header file being included more than once into your program, right? So every header file should have what's called an include guard, right? Traditionally, this is implemented using what's called a preprocessor directive, right? So we haven't really talked about the preprocessor yet, right? But when you write #include, you're actually using the preprocessor, right? So it's the preprocessor that reads the header file and sticks it into your program, right? The preprocessor can actually do a lot more than just include a file. So one of the things you can do is you can write conditional statements, right? So #ifndef means if not defined, okay? So this reads, if not defined, this name .2_h, where it's all in capitals. Okay? So for every header file, you're going to declare a constant that has the name of the header file in all caps, right? So .2_h in this case, right? So what this says is, if the identifier .2h is not defined, right, then continue processing this header file, right? If it is defined, then you're going to jump to the end of the if statement, right? So you just jump to the end of here. All right, so that's what the first line means, right? So it's just an if statement, right? The next line says define .2h, right? So if .2h is not defined, on the next line define it, right? So now the preprocessor knows there's something called .2_h, right? And now the rest of your header file goes in between the define and the end if, right? So the second time someone tries to include your header file into a program, right, the preprocessor reads the first line, right? Is .2h defined? Oh, yes, it is. So it just skips to the end and does not include everything else in the header file, right? So this is the mechanism that you use to prevent including a header file more than once in a program. All right, so the contents of the header file look like this, right? So here's my structure. There's my typedef, right, for .2, right? That says .2 is just an alias for struct .2. Here are all my function prototypes, right? So these, again, this is just like a Java interface, right? It's just the return type, name, and then the parameters of the function, followed by a semicolon. Right? So all this says is that there's some method called .2move that takes in a pointer to a .2, takes in a double and a double, right? And returns no value, right? So it says this function exists. It doesn't say what the implementation of the function is. It just says it exists, right? So when someone includes this header file, they're allowed to call this function, right? As long as they pass in a pointer to a .2 object and 2 doubles, right? So the compiler can check all of that. Right? .2mult is the multiplication function, .2 equals is the equals function, and .2 to string is my string function. Right? Notice that this thing returns a pointer to a car. Right? So C doesn't have any proper strings. Right? So in C, a string is just an array of car. So when you return a string from a function, you're just returning a pointer to some array. All right. So now I have a C source code file somewhere that contains the definition of these functions, right? Except for toString, these are all easy to write. Right? So here's my .2.c file, right? So I include all of the headers that I need. I actually don't need, yes, I do need those headers, right? And then I also include the .2.h header, right? Because that's where all of this stuff has been declared. Right? So if I want to start writing .2 functions, I need to include this header file. Right? When you include your own header file, right, a header file that you create, the name of the header file goes inside double quotes. Right? These less than and greater than signs, these tell the compiler to look in a particular place for those header files. So less than and greater than, it's telling the compiler to look in the standard place for any of the standard C library files, header files. Right? When you use the double quotes, right, that's when you tell the compiler where to find the header files. Right? So it's possible to put your header files in some directory somewhere and then tell the compiler to look in that directory all the time. right? For today's example, everything's in the same directory, so it doesn't matter. It'll always search the current directory for a header file. Right? So these go inside double quotes. Okay, so what does move look like? Well, move, you just add dx and dy to x and y, right? So that's easy, right? That's a pointer to a point to. So p arrow x plus equals dx, right? So add dx to px.